So for what I've seen so far, I think my talk will be slightly offset from the mainstream of what has been discussed so far. In fact, I will talk mostly, can you hear me well? I will talk mostly about the physics behind the cosmological and body simulations, trying to challenge the cosmological model itself. So how to implement basically dark energy and modified gravity models in n-body codes and how much this impacts the overall performance of the codes. So you all know the starting point from the science point of view. We observe an accelerated expansion in the late universe, and we have to try to make sense of it. So you are all familiar with Lambda CDM and how to run simulations in Lambda CDM. In fact, Lambda is the most popular and simple answer to this accelerating universe problem. But this is has very poor theoretical routings in some sense, and so many alternatives have been explored. And these are normally called either dark energy or modified gravity. And now I'll try to discuss what this means and what is actually the difference between the two. In fact, I will try to describe you two codes, or actually two packages that can be attached to the Gadget 3 code. One is called D-Gadget and the other one is called MG-Gadget, that cover together a wide range of dark energy and modified gravity cosmologies. But first of all, we need to understand what is the difference between dark energy and modified gravity. So a very popular way to distinguish the two is the following. You have Einstein field equations. Whatever change you make on this side, so on the Einstein tensor, you call it modified gravity. And whatever change you make on this other side, you call it dark energy. In the end, this is not actually a very meaningful distinction because you can easily demonstrate that modified gravity models are nothing than standard metric tensors, so standard general relativity plus a scalar. And the same is true for dark energy, where you have standard matter, standard energy momentum tensor plus a scalar. And in fact, it can be demonstrated that the two approaches are actually conformally equivalent to each other. So you can map one to the other with a simple conformal transformation of the metric. So what is a meaningful classification and the distinction between dark energy and modified gravity? Well, this only depends on the properties, dynamical properties and spatial properties of the scalar field. Doesn't matter whether you call it f of r or if you call it phi. And one possible classification, which I think is meaningful, is the following. You can classify your scalar, your additional scalar degree of freedom that is going to drive your accelerated expansion of the universe based on its time evolution properties, spatial fluctuations, and interaction properties. Okay, so cosmological constant is just the simplest case where you have nothing of these. Your scalar field is just a constant. You have no time evolution, no spatial fluctuations, and no interactions. And yes, exactly. Yeah. Sure. I mean, yeah, sure, of course. The cosmological constant is constant in density. But you can treat it as a dynamical field with zero velocity, in a sense, because then you get the equation of state equal to -1. That's the only way. So static. Okay. And you all know how to run cosmological simulations for this kind of model. But now you can make it a bit more complicated. You can have a scalar field which is dynamical, okay, so that has a speed phi dot not equal to 0, still having no spatial fluctuations and still having no interactions. And this is what is normally called dynamical dark energy, quintessence, k-essence, or stuff like that. This is very easy to implement in n-body codes because the only thing you have to do is you have to change your Hubble expansion rate. So you just change one function, you run your standard code, and everything works. But now you can make it even more complicated. You can have clustering scalar fields, which means a field that is dynamical and also has a small sound speed, which means that it clusters at subhorizon scales, still not having interaction, minimally coupled to matter. But in this case, it is more complicated, and this is still under development, so I will not talk very much about clustering dark energy. And then you have the most complicated case, which is an interacting scalar field, which is dynamical, has fluctuations, and is also non-minimally coupled to matter or gravity. These models are in general called either interacting dark energy or modified gravity. And I will try to explain you what is the difference between the two, which will be the main topic of my talk. So whenever you have a coupling between a scalar field and matter or between a scalar field and gravity, these source additional perturbations at subhorizon scales, which means that in your Poisson equation you will have an additional term here that is going to source the evolution of your structures. Additionally, you will have a fifth force, which is a term of this type in the acceleration equation of particles, which is driven by a coupling, which can be a constant or a function, Yukawa suppression term, which depends on the mass of the scalar, and the perturbation of the scalar field itself. Now, the complicated thing is that these perturbations here that determine this fifth force and this additional source term here obey a nonlinear Poisson equation, which is this one, which in general is nonlinear because this function is in general nonlinear itself, okay? So this is the main problem. You have to solve this equation along with your standard gravitational evolution. Now, a question should arise, because everybody knows that scalar fifth forces are tightly constrained. We know this since Brans-Dicke, okay? So scalar fifth forces should be ruled out. This is not entirely true, because these tests have been carried out in our local environment and using baryonic objects, okay? So actually, theoreticians have found two avenues to evade these constraints. One is to invoke non-universal couplings, which means that this coupling function is non-zero only for the interaction between dark matter particles and not baryons, which means that all the tests that you have done so far do not apply. And the other possibility is to have universal coupling and screening mechanism. Screening mechanisms are mechanisms through which this additional fifth force here is suppressed in our local environment, which means our solar system or our galaxy. Okay, so if you have universal coupling, this is what people normally call modified gravity, which means a universal coupling that is screened. And there are several possible ways to screen the coupling in high-density environments like our galaxy that have different names. One of them is the chameleon mechanism, which resorts on the fact that the mass of the scalar field becomes very large, so the field is very heavy in our local environment. So this Yukawa suppression term is very small, so you don't see the fifth force. Another possibility is the symmetron model, which resorts on the fact that the coupling itself becomes very small in high-density regions. Now, to have this kind of screening mechanism, you require large fluctuations of the scalar field, which means that this equation will always be nonlinear. So you have always to solve a nonlinear Poisson equation, and this is a very difficult problem. A few codes have been developed so far. Two of them are based on Ramses, Ecosmog, and ISIS. And one of them, which is the code I will talk about today, is based on GADGET. We published the paper recently on this, and the main developer is Ewald Puchwein from Heidelberg. Now, very briefly, what MG-Gadget does. So for the moment, we implemented only f of r gravity models, but this should be easy to extend to other types of screening mechanism because you just have to change one function in the code. So we have to solve this field equation, and we discretize this in position space. And this is solved using an iterative Newton-Gauss-Seidel relaxation scheme on an adaptive mesh. Now, you all know that GADGET is not an adaptive mesh refinement code, but what we do is that we use this trick. We can use the three nodes of GADGET as the cells of an adaptive mesh. And then we solve on this adaptive mesh. So it looks like something like this thing. So you can use the tree of the three part of the code as an adaptive mesh. Then the code also employs multi-grid acceleration. This is to achieve faster convergence when you map between different levels of the adaptive mesh refinement. And then basically, once we have solved for this degree of freedom, which is the scalar field on this adaptive mesh, we also know this quantity, which depends on the scalar field itself. And so for the standard Poisson equation, we can basically define an effective density, which comes from the fluctuations of the dark matter or matter density in general, plus the fluctuations of the curvature. And so we can solve this equation using the standard n-body solver, so standard 3PM algorithm of GADGET. We do this by associating an effective particle mass to this density fluctuation here, and then we apply the standard solver for the second part of the integration. So these are a few accuracy tests that we have done. So this is the point mass. This is the expected evolution with radius of the extra degree of freedom, this delta f of r. And the points are what we get from our simulation. So you see there is very good agreement. We have just some deviation on very large distances, but this is due to the periodicity of our box. So here we start to see replication of our point mass in our periodic boundary conditions. And this is a density peak test. So we have a density peak, and we try to see how well we can recover the expected evolution of the scalar degree of freedom, the expected configuration analytically found the configuration of the extra degree of freedom in correspondence of this density peak when we refine the level of refinement of the AMR grid. So you see here, these are different colors and different levels of refinement. And as you can see, we can recover very well the expected behavior. Okay, so this was for universal couplings. Now there is the other possibility, which is non-universal couplings, which means that you assume that the coupling is strongly suppressed in the interaction between the scalar field and baryons, so you don't have fifth forces on baryons. On the other hand, the coupling is present in the interaction between the scalar field and dark matter. Okay, so in this case, since you don't have to screen because you are not subject to solar system tests of scalar gravity like Brans-Dicke theory, you don't need to have a screening mechanism, so you don't need to have very large fluctuation of the scalar field itself. So you are allowed to have models, and in particular potentials, that give you very small density fluctuations of the scalar field. In this case, you can find approximate solutions, which anyway have been shown to be extremely accurate for this type of models, in which actually you can drop the nonlinearity of the Poisson equation that I showed you before, and you simply have to solve an additional Poisson equation that looks very similar to the standard Poisson equation. So basically, you have to solve two Poisson equations at the same time, but you can use the standard solver. Besides the fact that since you have a non-universal coupling, you have also a non-unique mapping between the Einstein and Jordan frames, which means basically that if you set up your variables in such a way that baryonic density is conserved, cold dark matter density cannot be conserved in moving coordinates. And as a consequence of this, you get an additional term, which is kind of a friction that applies only to dark matter particle. So this is the difficulty of these kind of models, which are definitely easier to implement in n-body codes than models with screening. But the difficulty is the fact that you have to follow two different types of particles, because the cold dark matter particles will obey this kind of acceleration equation, while baryonic particles will follow the standard acceleration equation. So they will not have extra fifth force and will not have a drag term. So this is definitely simpler and easier to implement than the model with screening I showed you before, but you need to distinguish different particle species, so you need to have multiple particle types in your simulation, and you need to implement a particle mass evolution, and in particular this friction term. So this has been implemented a few years ago by myself and collaborators in Gadget in a module that was called C-GADGET. And the D-Gadget code that I was mentioning before is simply trying to put together this C-GADGET module with the clustering dark energy part and with also scattering dark energy that I was mentioning before. However, so these two are still under development. Actually, when I subscribed to this conference, I thought I would be done with this, but unfortunately, I'm a bit late on the schedule. So in the end, what I will discuss today in terms of performance is mainly C-GADGET. So this is the interaction scheme. You must have multiple particle types. So you must have coupled and uncoupled particles, in this case, dark matter and baryons. And you need to treat them differently in your code. So you use the same Poisson solver, but with different gravitational constants for dark matter interaction and for all interactions that involve baryons, according to these different acceleration equations. On top of this, you have to add this friction term that comes from the fact that you have this kind of bimetric theory. This can be generalized to the case where you have two different types of particles with both non-zero couplings. Okay? In that case, you have both types of particles are coupled, but they are coupled differently, so you can have beta 1 and beta 2, two different coupling constants. And this means that there will be three different types of, let's say, three different gravitational constants, one for same interaction of one type, one for same interaction of the other type, and one for mixed interactions. And on top of this, the friction terms also will be driven by different couplings. So this becomes a kind of a more complex type of simulation in which you can even treat different particle types with different couplings, like for the Groningen neutrino scenario that I'm sorry I didn't have time to introduce, or multi-coupled dark energy scenario, which is a case where you have two dark matter families coupled with different couplings. So we have already a large number of interesting results from both codes. I will not spend much time on this because I want to say something about the performance of the codes. But for instance, what we found in the last years is that different interacting dark energy models can affect significantly the density profile of dark matter halos, especially at the high mass tail. So cluster type halos are significantly affected. and this can change the concentration mass relation of halos, especially at the high mass tail. Sorry? Yes, it is in both directions, and this depends on the type of model. So there are some of these interacting dark energy models that give you an increase of the concentration, and that depends on how the coupling function potentials are interacting with each other. And some models, actually, most models actually give you a suppression of the density profile, so a reduction of concentration. There are also effects, also in this case, they go in opposite directions, as you can see. In, for instance, CMB lensing, this is a quite recent paper by Carbone et al., in which we computed the lensing deflection maps through very large simulations that have been run with this C-GADGET code. And as you can see, you can easily distinguish these different interacting dark energy models because they have different imprints on the lensing power, both at linear and nonlinear scales. You see that there is this nice nonlinear feature here, but also at the linear level or mildly nonlinear level, you see that different models go in different directions. So you could use CMB lensing to try to test for these models. Or this is a recent paper I just submitted to Physics of the Dark Universe. There are multi-coupled dark energy models, this scenario I was mentioning before, in which you can even witness phenomena like halo fragmentation for some specific values of the coupling constant. These are funny models, but the interesting thing is that this value of the coupling here gives you a background expansion history and the linear evolution of perturbations, which is completely indistinguishable from the CDM. So the only way you have to distinguish these models is to go to the nonlinear regime, and you start seeing effects like these ones, and probably you can put constraints because you don't observe so many close pairs of objects in the sky. Results obtained with MG-Gadget. So this is, for instance, the effect on the matter power spectrum that is with respect to the standard general relativity. You see that different models with different values, let's say, of the effective coupling of the additional scalar field to gravity have different effects, I mean, different size of the effect, but also qualitatively are different because models that have a larger, let's say, models that are more far away from standard general relativity have a stronger screening mechanism. So the screening mechanism is more efficient in suppressing here the extra growth of perturbations at small scales, while models that are closer to general relativity have a milder evolution. And also you don't see very much turning point that corresponds to the onset of the screening mechanism at small scales. And this is also another interesting result. So with this code, we try to compare the impact of modified gravity on the matter power spectrum to the effect of AGN feedback on the matter power spectrum. And we found out that for some values, for some modified gravity models, or for some specifications of the AGN feedback model, they have comparable size and they go in opposite directions. So they are very likely to mask each other in possible observational surveys. So this is an effect that has to be taken into account when you want to achieve 1% accuracy in the determination of the power spectrum for surveys like Euclid, for instance. Okay, coming to code performances. So these are a few plots on the total CPU time. Don't pay very much attention on the scale here because these different plots have been obtained using test simulations that have been done on different number of processors with different number of particles. But in any case, of course, the range of models is always self-consistent, so it is always the same number of particles, the same number of cores, and the same machine on each plot. So what you see here is the model dependence of C-GADGET, which means all the simulations have been run with C-GADGET. And this is the computational time, in particular the overhead with respect to the fiducial case, which is lambda CDM, as a function of model. So you see, when you change the model, you get an overhead with respect to the standard lambda CDM, which is relatively mild. It's 25%, but still it's sizable. And but unfortunately, this is not all because, as I said, also the reference here has been run with C-GADGET. Now you have to sum this up to the overhead that you get when you run C-GADGET as compared to standard gadget, which is this. So as I said, in C-GADGET, you need to have two types of particles. So you need, if you want to achieve the same spatial and mass resolution, more or less, you need to have twice as many particles as in a standard gadget 3 simulation because you need to properly follow also the uncoupled baryonic component of the universe. So what you see here is a comparison of standard gadget 3 run with n particles, okay? The green one is standard gadget 3 with twice as many particles, and this is C-GADGET still with twice as many particles, okay? So you see that you get roughly, well, let's say this is the overhead that you get because you're running with the double the particles than in a standard gadget 3 simulation, and this is the total overhead, which is a factor about 4. So then you have to multiply this by the overhead I showed you before, which is about 20%. So, you can make the computation, but we need roughly, let's say, 5 or 6 times more for a C-GADGET simulation with the same spatial resolution as compared to standard gadget 3. This is the scaling. Basically, the code doesn't show any particular problem in scaling. So actually, we have very similar scaling to standard gadget. This has been tested. These are two plots that I prepared for a praise tier 0 proposal that was approved last year. And we tested up to 2048 cores. But now, at the moment, the code is running on 6,656 cores on Mare Nostrum 3. And so far, we didn't encounter any major scaling issue. We encountered other problems, a lot of other problems, but the scaling seems to be fine. Okay, now this is the same thing for MG-Gadget. Again, you see the model dependence. So this is, again, all the simulations have been run with MG-Gadget. And what you see here is how the computational time depends on how much the model deviates from standard general relativity. And you see that for this f of r 10 to the minus 4 model, you have the largest deviation, overhead of about 3.3. And this is the overhead with respect to standard gadget. So we run MG-Gadget in the general relativity limit. So this MG-Gadget run corresponds to this GR simulation here. And you see an overhead of a factor of 2.2, more or less. So this is the probably most relevant issue when you compare these codes is the memory allocation. So these codes require to allocate much more memory than standard simple lambda CDM simulation dark matter only. What you see here is the ratio to gadget 3 again of MG-Gadget with n particles. So the line here is a standard gadget simulation with n particles. What you see here is the same thing, same particles, but with MG-Gadget, still in the general relativity limit. So you see it's 2.5 times more memory you need. The situation is a bit better with the C-GADGET because most of the additional memory that you need is the one that you need because you're running with twice as many particles. So the additional overhead is relatively small. Okay, so this is a brief summary. I just put it here. So this is roughly the overhead in the memory allocation, which is 2.5 for MG-Gadget, 2 to 7 times larger than gadget 3 for the computational cost. And this is for global time stepping. So we forced the standard gadget to use global time steps. And this is likely to be worse than this for individual time steps, but the test for this is still running. For C-GADGET, this is roughly the memory allocation is more or less similar, 2.4 times larger than gadget 3. The computational cost is a bit, in general, a bit easier to achieve, 1.9 times. And the parallelism gives a comparable scaling. So in terms of whether we will be able or not to make a comprehensive program of large simulations using these codes, I think it will be possible, but very expensive, especially if we are aiming to simulations like the Euclid full-scale simulation that Fraser Pierce will discuss later on. I think we will not be able to run many simulations like that one with this modified gravity and dark energy code. So we need to find strategies to use smaller runs and to derive correction factors. How much time do I have? Is it over?
Yeah, pretty much.
All right. So I will skip this cosmic degeneracies thing, and I will just leave my conclusions here. I presented these two modules of the gadget code, D-Gadget and MG-Gadget. Actually, D-Gadget is incomplete still, so I presented only the C-Gadget part, but this will evolve into D-Gadget soon. That cover a wide range of dark energy modified gravity model. They have been robustly tested on basic test problems, and they give a very good accuracy results. And a lot of results, scientific results have already been obtained. The impact on code performance is relatively mild, but still probably it's not suitable for running a large number of cutting-edge simulations of these kind of models. And this is the point that I skipped. Since these modules are embedded into Gadget, it will be possible to investigate the degeneracy of modified gravity and dark energy models with a lot of other things like massive neutrinos, AGN feedback, and baryonic physics in general. So this is a very useful thing when we want to test our observables at the percent level, because many of these non-standard models like dark energy modified gravity, or even, let's say, somewhat more standard like massive neutrinos, might somehow be degenerate with each other and give us biased answers when we go and measure the power spectrum. Thank you.